Answer the following questions about these two reactions, X and Y. A. Is reaction X spontaneous under standard conditions? Justify with a calculation. B. Calculate the equilibrium constant for reaction X at 25 degrees Celsius. C. How will an increase in temperature affect K equilibrium for reaction X? Explain. And there'll be some more parts of the question on the next slide. Part D. Explain why the standard entropy change is greater for reaction Y than for reaction X. E. Above what temperature will the value of the equilibrium constant for reaction Y be greater than 1.0? Justify with calculations. F. For the vaporization of solid iodine, solid goes to a gas, the value of delta H at 298 Kelvin is 62 kilojoules per mole. Use this to calculate the value of delta H 298 for this reaction. Is reaction X spontaneous under standard conditions? Justify with the calculation. We're going to use the Gibbs free energy equation here, and if the Gibbs free energy is positive, the reaction is non-spontaneous. If it's negative, the reaction is spontaneous. If it is zero, the reaction is in equilibrium. So we have our equation right here. We plug in the value for delta H, which we get over here. Here's the temperature. And be careful with this one. Delta S we have to put into kilojoules. Okay, up here it's in joules. So you move the decimal point 3 places. We get delta G naught is minus 5 kilojoules per mole. Therefore, the reaction is spontaneous. Calculate the equilibrium constant for reaction X. We're going to take the value of delta G0 and substitute it into this equation and solve for K equilibrium. So before that, we're going to isolate K equilibrium by here dividing both sides by RT, then go E on both sides, and E to the ln just cancels out, and you get K equivalent is E to the minus G naught over RT. We then substitute in our values. That's delta G. Here's the universal gas constant, and here's the temperature in Kelvin, and we get the equilibrium constant is 7.53. How will an increase in temperature affect the equilibrium constant for reaction X? Well, let's look at Gibbs again here. Since delta S naught is positive, an increase in T will cause negative T delta S naught to become a larger negative number. That will reduce delta G naught. As delta G naught becomes smaller, the equilibrium constant will increase. Another perspective yields the same result. Since the reaction is endothermic, because delta H is a positive number, an increase in temperature shifts the reaction to favor more products relative to the reactants, resulting in an increase in the value of the equilibrium constant. Explain why the standard entropy change is greater for reaction Y than for reaction X. The increase in the number of moles of gas in reaction Y is greater than reaction X because reaction Y begins with no gases, right, just a solid and a liquid, and reaction X includes a gaseous reactant. They both have the same number of moles of gas as products, therefore the standard entropy change is greater for reaction Y. Above what temperature will the value of the equilibrium constant for reaction Y be greater than 1.0? Justify with calculations. The equilibrium constant is equal to 1 when delta G naught is equal to 0. According to the Gibbs equation, delta G naught is 0 when T delta S naught is delta H naught, right? You make this a 0 and you get that. Substituting the entropy and enthalpy values from reaction Y into this equation, and you find that the temperature is delta H naught over delta S naught, and we have here delta H naught, 41,000 joules. We're converting from kilojoules to joules in this case because our delta S is in joules. You can do it either way as long as you're consistent. So the temperature is 330 K. Because the equilibrium constant is equal to E minus delta G naught over RT, as the temperature increases, the equilibrium constant also increases. Therefore, when temperature is greater than 330 Kelvin, the equilibrium constant is greater than 1. For the vaporization of solid iodine, we've got a solid going to a gas, the value of delta H298 is 62 kilojoules per mole. Use this to calculate the value of delta H298 for this reaction. Well, we're going to use Hess's law, and we've got reaction X up here with the delta H and the delta S. And we're going to combine reaction X right here with the given equation right over here. So here's X, here's the given equation, and when you add the two together, you get this equation here, which is what we were looking for. So we take the delta H for the first one, and we put a 2 in there because of this 2 right here. Here's minus 62 joules per mole for the given equation. Add them up, and we get a delta H of minus 26 kilojoules per mole.